Okay, so today I'm talking about a digital representation of 3D object. I supposed to talk about the pipeline in lecture 6, but I changed a bit the program because this allows you to progress faster with the project, and I will talk again about the pipeline in the lecture number 9, just before I show the shaders. I think this is a much better flow. So now you get more into what is a digital representation of 3D object. So this is very important because it tells you how an object, like a mesh usually is called, also in Three.js, is represented into the machine, and how you can actually load it and include in your application. So what is a 3D model? 3D model, it's a mathematical representation of a 3D object, right? If you have a shape in 3D, so it may be a continuous like surface, it may be everything that you want to represent, and actually a 3D model is a mathematical representation. So it's a way to represent this in a 3D space. Somehow it's possible to render and to manipulate by the machine, okay? And for example, here you see like this teapot, which is very smooth, and you have also a mathematic function on top of that that tells you like the parametric line of this meshing. So there are two possible usage of models that you can imagine. There are like offline applications. For example, I want to do a rendering and with a ray tracer, and I have a very high detailed mesh with a lot of details, and I just do ray tracing. So I shoot a ray from the point of view and then I render it pixel by pixel and getting the nice effect. And to do so, actually I can use a very high resolution mesh because it's offline, but for what is interested to us, it's a real-time application. So it means something that you interact with it, and so it should have a decent resolution, not too many triangles, because we'll see the mesh are represented by triangles, by geometric primitives, okay? So the thing is, like, it doesn't really necessarily mean that the final rendering it's bad. It's not as detailed as the other, but in the end there are a lot of tricks. For example, here you see in this car what is called environment mapping. So these reflective lines on the surface of the car is the reflection of the environment surrounding the car. Or for example, you can put textures, colors, or kind of materials, which doesn't mean necessarily you have to do ray tracing, but there are a lot of tricks to make it nice. And in Unity, all these tricks are implemented. Here you will understand what's behind that. And yes, again, here, for example, you may see like this is a kind of old video games, but the result it's pretty much the same, and also like a movie which is the last Jurassic Park, I think it's some years ago. And so of course the T-Rex model is much detailed on the left side, but it's not like that. It's also like the lighting environment is much more complicated because you are actually doing ray tracing, while on the right side you have a real-time application. So you need a model which is capable, for example, to move freely in the scene. So instead of doing some predefinite movement, it has to move freely in the scene, so it has other difficulties. So the movement is not predefined, and also the amount of triangles and the amount of the details of textures are much lower, right? But still you can get nice results. And of course, given a 3D model, you can have static models like a sculpture, and this is pretty much your case for the application that you are developing. But there are also animated models which are much complicated because involves usually when you animate a model in 3D, you actually don't have just a 3D model and you don't move a vertex in every possible position. What you have a skeleton inside the mesh, and the skeleton moves, and the vertex are linked to the skeleton with certain weights, okay? So it's actually, imagine your body, you move the bones, right? The muscles deforms, the skin deforms, the same principle, okay? So it's actually, the user, they program the movement on the bones, and then all the shape will follow. But again, this is a bit more complicated, so in your application that you have to develop, static mesh are fine, okay? There are also other, there is another difference between 3D object, 3D models representations. For example, you may have like volumetric based representation. For example, you may see that this element here, it can be is of course a surface, right? But how you can represent this surface? Well, you can see, okay, you know what? This surface is like the the intersection. I do the intersection between the cube and the sphere, and I get this, right? I do the intersection between these two cylinders, I get this. I get the intersection, the union, this is union, and then I do subtraction of this plus this, right? These are called Boolean operation also in 3D, and actually, finally, you define a mesh with a set of operation, you define a geometry, and this kind of representation is called constructive solid geometry. And of course, the amount of things that you can do, it's limited because it's only like operation with implicit and very basic shape representation, sphere, cylinder, something that usually you can describe mathematically in a precise way. So write the equation of the sphere, write the equation of the cylinder. Of course, you cannot write the equation of a skull, right? Of this kind of mesh, which is much more complicated, or the mesh on the right. So the mesh on the right is the example of boundary-based representation. What does it mean? Is actually you have a set of vertices which are interconnected by polygons, right? Here you can see there is a boat which is made by a set of polygons which are not really triangles, are generic polygons. Here you have a mesh made by a quad and also a mesh made by triangle. So a little digression. So usually the mesh that we will work with, they will all made by triangle in general, but there is a lot of effort and a lot of research, and it's very important getting this quad mesh that you see here. And the reason is that when you have a quad mesh, so the artists, I mean like modelers, when I talk about artists, is modelers that do like animate characters or animate faces, they actually prefer to work with quad model because because on a quad model you can define what is a subdivision surface. So given that quad model there of the hand, you can define precisely a smooth surface, infinitesimally smooth, given that base made of quad. You can define a function which is like that, which allows the artist just to concentrate on a few patch and orientation, and then, for example, you have a face of a character made of a few patch, and on top of that you can have precisely this description of the smooth surface of the character made of a lot of faces, which will be inferred automatically given this base mesh of quad. This is called a subdivision surface, and usually what you need is a mesh of quad. And obviously, since the quads, as you can see here, they follow what we call the principal curvature lines. So for example, you can see in the hand the lines, the quads follows the features and follows the direction of the fingers, and you can do this only with quads because quads have two directions and they can align very well to features. So what happens is, like, when these things deforms and the animator do the animation, so the resulting deformation will be much better without artifacts than the one by triangles. This is just for you to know what happens in the animation and in the modeling community. Of course, we don't explain subdivision surface in this course. It's a lot of math, and I don't want to scare you, but yeah. And of course, there are also other mesh like 3D models definition. For example, coming back to the volume based, if you consider the volume like the solid volume, you can do like algebraic operation, constructing solid geometry, or you can have, for example, the result of a CT scan, which is already a 3D object, but instead it has some volumetric information, right? And the other one on the right is some model of volumetric texture with a bone and some result of a simulation, for example, heat transfer on something. Okay, so this just to give you a bit of introduction, and so there are, for example, there are two different kind of mesh. There are triangle mesh. Sorry, the title is misleading. It should be like mesh classification, okay? Not quad mesh classification. So there are triangle mesh, which are, so these are the most common mesh that you find in around, right? Of course, there are also mesh with face are made by polygons, but usually what you have is you have triangle mesh, which are the one that you're gonna use for your project, where all the face have 3 sides, and then there is quad mesh, where all the face have 4 sides, and there is also another category which is called quad dominant mesh, where most of the face have 5 sides, and then there is a few face with 3 or 5 sides. That's also very useful, and when you download the model, it can happen that you end up with something like that. Should no problem for 3JS. What I suggest is to open in MeshLab and save as apply, so that it becomes a triangle mesh and it's much easier to handle. Again, what I have to say for the guy that wasn't here at the beginning of the lecture, so I actually, if you go to my website, so there is under teaching, I actually did a video about how to include the model in the scene with me narrating everything. It's a bit long, but it's also include how you download the model from TurboSquid, how you can reduce the number of phases, how you save it, and finally how you include in your application. Okay, for the others that are again not present at the beginning, I actually also did another application which may be useful for some of you. This application I will do also a video of narration of this instead of explaining you now at lecture, so you can actually see the video and carefully understand what happened, and also you can download the code, of course, and the idea is like this application, it allows you to load the model, define a normal map, which is this kind of textures that show different lightings when you move it, and then you can click on an object and put on different position, which is maybe useful for you to get inspiration for your own project, where you actually, for example, have to model a house or have to model a museum or whatever. Okay, so this to make your task easy, and instead of doing the code today, as I said before, it would be nice if some of you very the most prouds, prouds will come and show me the current status of the project, even if it has bug, even if it's not complete. It would be nice so we can discuss and I can help you, and my help can be shared by everybody. So that's supposed to happen at this lecture, okay? So let's come back to the slide. And also I am actually recording this lecture, which will be online for the people that cannot attend the lecture because it was too early. So I hope all the recording will work fine. Seems so. Okay. So coming back to the mesh, what is a triangle mesh? Okay. So in general, you may think about a triangle mesh as a set of triangles that share the edges. So for example, this is like this solid, which is a platonic solid, and then I don't think this is a platonic solid anyway. So these have maybe 12 faces. Then you have a set of vertices, right? Vertices are points at the end of the triangles, and that defines the geometry. But this is not enough to define the geometry. You have also a set of faces, right? Each face, in a case of triangle mesh, interconnect three vertices, okay? So you may already trying to think about what is the data structure to represent this kind of data, this kind of what is called a mesh, right? A mesh is like that. When you define in Three.js a cube, a box, or when you define a sphere, what Three.js does, it creates automatically something like that. And if you load a mesh, you create something. You load the mesh, and then in memory it creates something like that, right? And in the example that there is linked into my website, there are two important things. One is how to load a model and put the model on the scene. The other is how you can define a model by itself, yourself triangle by triangle, which I believe is important for the people who do, for example, the terrain generation, that you want to move individual triangle to a certain position. So in the example you will see on the YouTube file, there is I am actually creating a mesh and generating some noise on the surface of the mesh, and then you can tune this noise to make your terrain, right, or whatever. Okay, so this is very useful for people who have to load the model, and for people who actually want to do the terrain generation project or other project that you actually want to define your mesh instead of just loading and you want to manipulate it. Anyway, in the end, you have a set of edges, right? Edges are between pairs of adjacent face, and in the end, you actually close an object, right? You have an object which is closed, and then next lecture we'll see a bit more of math and topology of the mesh, but and we'll see what is a border and several characteristics of a mesh. But right now, to help you to progress with the project, so now you have an extra week because there is no lecture next week, so then you can focus and do everything and push your project far, okay? So okay, a mesh is a set of triangles that share edge, and the position and the geometry of this object is identified by the position of the vertices. Okay, so again, why we are interested into triangles mesh and why there is also quad mesh in general, I explained to you at the beginning. So as you can see here, it's very, very intuitive what happens, right? You have the same geometry, and on the right side is a triangle mesh, which is usually what you get when you use a 3D scanner. So 3D scanner are like device that allows you to capture an object in 3D in real world and to bring into digital world. Even the Kinect of Sony PlayStation, I think it's a kind of range scan device, and it can produce this scanned meshes, and by the end of the day what you get is like a soup of triangles, unstructured, right? So this mesh is nice for our application that you basically have to do rendering, but for other kind of application where you actually want to animate the mesh and you want to put a subdivision surface on top of the mesh, as I explained, it's maybe better to have something like that on the left, which is a quad mesh, which usually 90% of time are modeled by hand, right? There is an artist that starts with a cube and extrude and extrude and extrude, and eventually it ends up with a dinosaur, okay? But of course, what happens if you have a quad mesh, you can always transform into a triangle mesh simply by splitting the quad into triangles. And actually what happens, when I explained to you the pipeline, right? The pipeline is all based on triangles, and when you actually interpolate quantities like normals, for example, for the Phong shading, right? Or colors for the Gouraud shading that I explained to you last time. So what happens is you have to interpolate inside the triangles, right? And I will explain you why. But actually, if you have quads, so OpenGL automatically do this split. So you should be able to load also quad models in your application, and that should go like smoothly. In general, if you have a polygon, you can tessellate into n-2 triangles, with n is the number of edges of the polygon. If the polygon is convex, this is very easy. If the polygon is concave, this becomes much complicated. This just to tell you that it's always possible to transform a polygonal mesh into a triangular mesh. Of course, it's out of the scope of this course to explain you like geometry processing algorithm to do so, but just to know that it's possible, okay? This is not easy in the general case. So, okay, so what is a polygonal mesh in general? You can define it as a piecewise linear approximation of a continuous surface, right? It's actually complex words. That means a simple concept. So you have a continuous surface representation like a sphere, for example. You can define a sphere with a mathematical function, okay? A function of x, y, z. So this is a continuous surface, right? Infinite precision. So each point of the sphere you can actually define precisely with infinite precision, because it's the result of this equation. It's like in 2D when you actually define the circle, the equation of the circle. When you actually did analysis, right? You can define the circle, the function of the circle, and then in this way it's implicitly defined, and each point has exactly the right value, right? But you can represent the circle as a set of segments, right? A set of segments, one after the others, that create the circle. But this is a piecewise linear approximation of the circle, because each interval is a line, okay? And similarly, the same concept in 3D, you can approximate the sphere, which is an implicit surface, and you can define with a function with infinite precision, with a set of triangles that are planar. Each triangle is planar, okay? But they approximate a sphere. So in reality, you are committing, like, you are doing an approximation, right? Because it's not a sphere, because the triangle is not curved, the triangle is flat, okay? So you are approximating the sphere. As more triangle you put, the more approximation you get. So this piecewise linear approximation of a continuous surface means like that. And 2D manifold, why? Because a surface is basically, even if it's embedded in 3D, it's actually 2D, right? You can imagine as a piece of paper where you have two directions of the surface. It's not, the surface is embedded in 3D, right? But the surface is actually a 2D object, right? Because it has no thickness. It's only have like it's flat, right? You only bend it and you create a surface. You create a 3D surface. Okay. Anyway, so the components of a polygonal mesh, two main components. Then there is also attributes that I will explain you. There is vertices or geometry, what is called also in Three.js, which is the position of each point on the, so each vertex has a position x, y, z, right? And it identifies the position of the object in the space, and it's a way to sample this continuous surface. For example, you sample the sphere and you have this set of points, and then these points are interconnected by triangle, and this is called like a connectivity, right? All these two things, they compose a mesh, right? This is usually not enough. Sometimes what you need some extra information, for example, colors, or for example, let's say like normals, right? You remember you have normals per vertex and normal per face. Of course you can compute, but you can also store you have to store in the mesh, right? So if you have normals per vertex, for example, your class that maps the vertex should have an extra attribute that is the normal on that vertex. Or if you have normal per face, your face class should have an extra attribute that per face you have the normal. You remember the normal? I hope so, right? It's the vector tangent to the surface that you use for like creating the lighting of the object, okay? You can also, for example, variate the material. This is not the case for our Three.js object, but you can also variate the materials on the surface. So different face can have different materials. I suppose it's possible to do also in Three.js, but it's we don't want to explore these things. Also colors, you can associate colors of different points of the surface, right? This is in general when you have a mesh representation. So again, this is much in detail. So you have a set of points, right, in the space, and of course, again, these positions are expressed in object space, right? Everything that is in the mesh is in object space. So it's in the space the artist modeled the object, right? It's not the space of the scene. It's the space that the artist modeled the object. If you see my actual example that I put online on YouTube, you can understand how you can bring an object which is huge and somewhere into your scene in a precise location, okay? And then you have a set of triangles that create this graph. And let's say, like, for example, you have attributes for each vertex, for example, colors. It can be also normal, right? Can be also normal per vertex. So why we need a triangulation? Because, for example, then you can interpolate the values inside each face given the one on the boundaries, on the vertices. This is, for example, as I explained to you, for the Phong shading and the Gouraud shading. So one interpolate colors, the other interpolate normals, but on the triangle this is well defined, how to interpolate things, quantities from attributes on vertices. So the idea is like that, right? When you sample something on the vertex in general, or in OpenGL, when you define an attribute for each vertex, you implicitly think about that attribute will be smoothly interpolated inside the face that shares this vertex, right? When you actually instead define an attribute per face, what do you mean is like this attribute per face is constant within the face. You remember flat shading? Flat shading is normal constant per face, right? While Phong shading, the normal varies inside the face, and Gouraud shading, the color varies inside the face, right? Given the light computed on the vertices. For example, here it's like example, you can interpolate colors on normal, and the idea is like how you interpolate values inside the triangles. There is a concept that is very well defined. There is a way to derive this, what is called barycentric coordinates. So barycentric coordinates is a set of coordinates that the barycentric coordinates, for example, of P within this triangle are a set of 3 values such that the multiplication of these weights for each position of the vertices, it gives you this position of P. So for example, if you say let's say P has barycentric coordinates A1, A2, A3 within this triangle, so that means that if you actually that you can express the position of P as A1 times V1 plus A2 times V2 plus A3 times V3. So why this is important? Because by variating this, and another thing that is not written here is this barycentric coordinate, of course. So what is this, right? This is a weighted average, right? It's when you average something, you usually do, what is the average between 10 and 5, right? 7.5, right? Because you do 0.5 times 10 plus 0.5 times 5. But if you change this weight, what you do is like you do a weighted average, right? It's not A plus B divided by 2, but it's A times something plus B times something. And these two quantities, they always sum up to 1, okay? This is weighted average. Simple concept. I think you already know, I suppose you already know. So this is a kind of weighted average in 3D to express each point into the triangle with these barycentric coordinates, right? So that means that if you variate these barycentric coordinates, you are able to move inside the triangle smoothly. And these weights, they sum up to 1, okay? So, and in principle, what happened is like, coming back to our pipeline, so, and explaining you why this concept is important before to go on with the mesh, is the fact that suppose then you projected your triangle, you do all the stage, and then you are at the end, then you, for example, implementing the Gouraud shading, and then you actually have the color on each, or the amount of the lighting on each of the vertex, right, on the side of the triangle. So these are pixel, okay, pixel, because it's the last stage of the pipeline where the triangle is projected on the screen. And then you have to retrieve the color for the vertex in the middle, okay? So what you can do is actually compute the barycentric coordinates of this vertex and then interpolate the color using this formula from the others, right? So this is what the GPU does to interpolate quantities inside the triangles. So at the last stage of the pipeline, it actually interpolates variance, which is attributes per vertex inside the triangles. So you have, then what you have something like this, okay? So suppose each triangle have like a color here. Suppose this color maps the normal RGB, okay? So what you do is like when you project this on the screen and you have colors on the vertices, and inside they're interpolated using this weighted average, and because each point inside the triangle has its own barycentric coordinates, we will end up varying smoothly, okay, on the surface. So here you can see again the pipeline and the different stage, and of course it's what we have seen so far, and we will see much better in the last lecture. Yeah, for example, you can interpolate normal if you do like Phong shading, right? And at the end you apply the lighting to obtain shading. So if you do Phong shading, if you remember, you interpolate normal within the triangle, and in the end what you get is like something like this, right? Suppose RGB is the normal, this varies smoothly. Okay, so coming back to triangle and polygonal mesh, we have seen the digression of why, one of the reasons why triangles are important, because they allow us to interpolate quantities smoothly inside the triangle from quantities on the vertex, which is fundamental for the GPU processing. Okay, so actually the resolution of a mesh, what is? It's usually number of phase or number of vertices. Usually we will see in the next lecture I will talk about Euler characteristic, which is a mathematical concept which relies number of vertices and number of phase of a mesh. In general, what you have is like number of phase is 2 times number of vertices. So it seems counterintuitive sometimes, but it's you can try to count, and this is the case, okay? Believe me. And of course, I mean, if you have high resolution mesh, which means usually you consider number of phases, right? Because number of vertices are a consequence of number of phases. So if you have a high resolution mesh, then it's more accurate, the rendering, but of course it's the frame rate of your application. So it means the frame, you know what is frame rate, right? It's the amount of times like your application can refresh the view in 1 second. It's slower, while with low res mesh it becomes more efficient and you have a higher frame rate. So low polygonal mesh are used usually for games. I mean, if you have a nice low polygonal mesh modeled by a user, you can put texture on top of it. You can put normal mapping. You can put bump mapping, all techniques that we explained at the last lecture when we talk about texturing. But in the end, what happened is, yes, I mean, you can get pretty decent result, but you see still there are like, I mean, for games and the interactive application, that's pretty fine. Okay, so what is the typical resolution of a mesh, right? So back in 1994, there was this famous mesh that has been scanned, and you will see in all papers of computer graphics. It's called Stanford Bunny. Why? Because it's been acquired with a 3D scanner at Stanford, and there was like 70,000 triangles. For the times that was okay, there was, you can do pretty decent shape, and then you can see like you really have enough resolution, and most of the triangulation is even like you can even do even much more detail, okay, with that. So, but then in 97, so the resolution has scaled up exponentially, right? So because the GPU became much more powerful, and because, as I explained in the first lectures, GPU are basically a set of parallel processor, right? How you can augment the power of a highly parallel processing unit. How you can simply augment the power, right? I have 10 units that works in parallel. Instead of 10, I put 20, and then I have double the power. But because it's completely highly parallel, and each triangle and each vertex is processed independently, right? I can do it. Then from 20, I put 40, 80, and I can grow it exponentially. The only thing I have to take care about, like, to cool down the GPU, right? Because sometimes get like you have overheat, and this points to like get much more resolution mesh, and then in the end you get like 2 billions model in 2002. For example, the David in Florence sculpture that has been acquired. and you can see like it's very detailed, right? Of course, the revolution in this is like not only the GPU power of rendering it, it's also like the acquisition device, 3D scanner that becomes more like accurate, and also like a set of new tools and computational power to handle this, right? To like create a triangle mesh, not just visualize it from the 3D scan. Okay, so of course, as I said, if you increase the quality, then you decrease the performance. If you increase the performance, then you decrease a bit the quality. So it's always like a matter of finding the right balancement for your application. And yeah, of course, the resolution is not uniform everywhere, right? You can have mesh that has adaptive resolution. So for example, if you see the video that I actually posted on my web page that explain you how to load the model and the whole pipeline, I suggest you to do so when you code in the next, because you have time to push your project, you have 2 weeks. And so there I actually download the model from TurboSquid, and then I realized, oh, this model is way too big for my application. It was like a lot of several millions of triangles, right? And maybe it's too much. So then what I said is like I imported in MeshLab and I did like quadric edge collapse decimation. And you will see in the video, it's all explained in the video, linked on my webpage. So you can go there and look it very carefully and enjoy my Italian accent. And that's it. Yeah, I realized that I have a strong Italian accent when I actually listen myself speaking in the video. So, but that's fine, right? Anyway, so what this quadric edge collapse decimation does is actually reduce the amount of triangles, trying to keep the same geometric fidelity, right? The same, and to introduce as less error as possible. So to keep the same accuracy. So here there is an intuition about that. Of course, if where it's flat, where it's basically flat, you don't need a lot of triangles. If you have to represent a flat surface, basically like a flat quad, basically you just need 2 triangles, right? It's flat. Why then I have to put more triangles? Nothing changed. But if you have details, for example, on the tail rain, where the rain bumps, maybe you need more triangles. That is difficult to implement, is adaptive resolution, but just that you have to know that there is these things, right? And of course, I mean, for the guys who will implement the project of terrain, this is not required. I mean, it's like just uniform resolution over the terrain is fine. But just have to know. So, okay, there are several ways of like encoding a mesh. So, for example, when you actually print a model and you put a model on the 3D printer, what you actually see usually it's SDL format. SDL format is the most common format used for 3D printed. And how you encode the mesh? Simply, each triangle is a triple of 3 coordinates, okay? So instead of having like the vertex by itself, so you have each triangle is XYZ, 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 3 different coordinates. Of course, what happens? It happens that since triangles share a vertex, usually in a triangle mesh, one vertex is shared by 6 triangles in average. What you have the same vertex referenced multiple times, or like you have a lot of wasted space, right? Because you have a lot of redundancy. You have redundancy with this kind of representation. Okay, but this is very simple and straightforward, and it's used by 3D printer. Okay. There is another method. It's called indexed. Sorry, I have to change one word. The thing is like you have the idea is like instead of having like tripole of positions, you have an array. So you know what is an array, right? A vector, right? You know, I think you know because you actually did some programming of vertices, and you have an array of triangles, right? So the triangles, each triangle is a tripole of indexes, okay? So it's 3 index, 3 integer. Each one, it tells you which vertex refer to, right? So in this way, you don't have redundancy. That's clear? So we can see an example here. For example, it's very simple, very, very simple. So you have a vector or an array, depends how you call it. In C++ are two different things, but let's call it array. So then you have an array of vertices, then you have v0, v2, v3, v4, and v5, right? Each one has its own xyz coordinate plus some attributes, let's say the color on the vertex. It can be also the normal on the vertex for shading purpose, okay? And then you actually have another vector that explain you the connectivity. For example, T1, how is formed T1? T1 is formed by, for example, V4, V1, and V2, right? These three vertices. And T2 is formed by blah, blah, blah. And these actually are index of the vertices, okay? It's clear? It's pretty easy, right? So the only thing you have to take care here, okay, so you may have a question right now. You say, okay, what's the difference between saying like instead of T1, instead of being V4, V1, V2, it's V1, V2, V4, or it's V4, V2, V1. So what is the difference? Okay, so the only thing that matters is the order, not the order, the orientation, right? So if you put like V3, V4, V1, V2, and V1, V2, V4, it's the same, right? But if you change the order, V2, V4, V1, it's different. Sorry, for example, V2, V1, V4, the opposite. So suppose they're rotating clockwise, and then you actually list them in counterclockwise. What does it change? If you remember how we compute the normal, okay? How you compute the normal? Exactly, right, perfect. So you change the orientation of the normal, right? And what happens is like, if they rotate in the same way around the mesh globally, all the normal will point all together outside or all together inside. So you have a coherent orientation of the mesh, okay? Again, when you actually load the mesh from Three.js, this is implicitly done by them, but if you go in your project and you define triangle by triangle your mesh, you have to be careful that the orientation is the same, okay? When I talk about orientation, and I will show you later, like the intuition is like the edge, for example, between V2 and V4, right? When you see from triangle T1, you pass in one direction, right? When the edge that you see, the same edge as seen by T2, you go in the other direction, even if they rotate in the same sense, okay? So that's another way to see that. And this is because of the normal. Great. I'm glad you understand this thing. Okay, so let's see a bit about memory occupants. So then you have actually, for example, this is a quad mesh, right? Instead of a triangle mesh, essentially is the same. You have a list of vertex with coordinates. So sometimes the first vertex in some format is referenced as vertex 0. Other format vertex is referenced as vertex 1. Of course, when you define a mesh on JavaScript, first element of a vector is element 0, right? And also in C++, okay? But there is some format which may be misleading. For example, OBJ format or there are two main formats that use this kind of representation, OFF and OBJ. OBJ is start from 1. Don't ask me why, but the first vertex is 1, and you keep getting crazy if you write your own processor for OBJ file, because it's not intuitive for somebody who programs in C++ or in JavaScript. Okay, so and what is the memory occupants is very low because it's kind of the minimum you can use, right, without any redundancy. It's like 3 unsigned int per phase, unsigned because you don't have negative index, you have from 0 to max int, and then 3 scalar per vertex. So floating point or double that tells you the coordinates. Okay, and for example, here you have a representation of the OFF file. Sometimes when you download from TurboSquid a mesh, the format is like, usually most common formats are OBJ and OFF. There is also 3D Studio and other, but these are formats that are proprietary of the Autodesk, right? Or the like the guy who actually did the program itself. So here you can see like you have a list of positions like X, Y, and Z, and then a list of phase. Okay. Good. Now, so yeah, going more into detail. So here it's explaining you better, but just to tells you how this is stored. So usually at the beginning of a file, even like in OBJ, I forgot to mention it, there is number of vertices, number of faces, and sometimes number of edges of the mesh. Even if edges are not encoded implicitly, sometimes there is, right? It's like it's the format. And then you have XYZ of the vertex. In this case, it's a second vertex, for example, 300. Okay, and then you have 4 vertices of the face, right? So in OFF, the first number is the number of vertices of the face. So in this case, is a face with 4. So you see, like you have 12 vertices. If you count, you stop there, right? So the last entry with 3 number is the coordinate of the last vertex, and then you start with the face, right? And the first number is the number of vertices, and then you have the index of the vertices. And of course, in this case, the first vertex is referenced at the index 0. So this is not the case for OBJ, but I mean, you don't have to develop this. It's just you have to know how these things are stored. Of course, this is good because it's very GPU friendly, because it's the same way that you actually, the GPU, I didn't explain you that because there is no time in this course, but when you actually send a mesh to the GPU and you send a set of triangles, what you do, you don't send one triangle by the time, but you create a package with all triangles, with all the vertices, and then this is done by Three.js. You don't see that. And then it stores on the GPU, right? And then it comes on the GPU memory. You don't have all the time to go back and forth to the bus, okay? And this is like similar to the way that GPU store indexed. And of course, the bad is that, I mean, smooth surface can be approximated because you have a set of face, but this is all for polygonal mesh. Okay, let's see now something more general, because sometimes you may need some more information. So what you have in the mesh is like vertices, edge, and face, okay? So for Three.js, what you need to know, it's already there, right? It's like indexed mesh, right? But in general, there are other mesh representation that allows you to do like some manipulation operation, modeling, okay? So the entities that you have in a mesh, it's vertex, face, and edge, right? And then you have you can implement a set of queries. For example, give me the vertex close to another vertex, right? Which is called vertex-vertex adjacency, right? For example, you have the yellow vertex and you want to get the red one because you want to do some processing on the mesh. Or for example, give me the edge that are close to the vertex, or give me the face that are close to the vertex, right? So with our implementation of indexed mesh, the only thing we have is for each face the vertex, right? Because you have an index of, for each face you have a list of vertex. So the only relation you have is face vertex, okay? So if you want to do other, so for example, given a face, if you want to get the face which is next to another face close to an edge, then you have to implement other structures. This is not your case, but maybe you may need. So then you have to implement a map, for example, or something on top of that you instantiate in memory, and that tells you like, oh, I have this face along this edge, my next face is this other, right? Or I have another face, or for example, for this vertex, what are the other vertex that are around, right? Or for each vertex, what are the face incident to the vertex. Of course, if you have this one, if you have vertex face, then you can retrieve vertex vertex. So some of them, they are redundant, but when you have a couple of tables, for example, if you have vertex face, right, that tells you what are the face incident to a vertex, and my query is, okay, give me the vertex which are close to mine, like the star is called. So what you have to do is like getting the face, and then rotate, and for each face look to the other vertex, and I remember you have this, right? So for example, you have this vertex, right? Then you get this, and this face, and then for this face you can use this relation to get these, and this vertex, which are actually vertex-vertex relation. So the star of vertex next to another vertex. So if you need to do so in your application, then you need to create an additional data structure. This is not your case, but unless you want to do something like of mod processing. But this is some of the basis of the modeling, right? For people who do mesh modeling and manipulation. Okay, so when I say, like, for example, what is the next face adjacent to an edge, right? So the edge can be from a global point of view, or can be also intended from a local point of view, right? If you remember here, when I create this this one, I can say, okay, this triangle has v4, v1, v2, right? So I can say, okay, so then for this triangle, this is the first edge, this is the second edge, this is the third edge, seen by this triangle, okay? While for this triangle, for example, if it's v4, v2, v5, so then this is gonna be the first edge, the second edge, and the third edge. So the edge can be seen also from a local perspective, right? So if I see an edge, if I see an edge, I can say, okay, from the point of view of this face, right? If I take a face, if from the point of view of this face, this is my first edge, this is my second edge, this is my zero edge, right? If I start counting from zero. And the idea is like, for example, you may say, okay, I am on face f0, what is the next face along edge 0? And then you get f1, okay? But it's a local perspective. And this comes out to the fact that, again, this local perspective on the edge, so how you consider the first edge, the second edge, it's implicitly defined by the order of the vertices, right? And it defines you the orientation, okay? as you noticed, the orientation has to be coherent because of the normal, and if you try to make it coherent, what happens is like two neighboring faces, when they share an edge, the edge is going in one direction from one face and it goes in the other direction from the other face. You can try to draw something like some two polygons, right, and list the vertex counterclockwise or clockwise, and when you pass the same edge, they will go on one sense on one and on the other sense on the other, right? Okay? And for example, in this case, this is, if you consider this face and this is the first, second, third, and fourth edge. It depends about how you list in your order. Okay? Yes. So you see, this is the orientation. Okay? So just again to make everything clear. So you have, for example, the first is ACD, okay, and then the second is ABC, okay, and if you see, like, they always rotate in clockwise manner, okay, even if in one sense you have AC and the other you have CA, right? You may think this is a cycle, right? When you have C and then you have A, like that, right? So in one sense you go in this direction, in the other sense you go in the same direction, but you pass the edge into different ways. And of course, this is edge 0, this is edge 1, this is edge 2, this is edge 0, edge 1, and edge 2. It depends about the order. Edge from a local perspective of a face. Yes, that's exactly the concept that I was explaining. And for example, when you actually have a mesh, in general, you have this coherent orientation. And the normal will point on the right direction. Okay. And as you noticed, actually as she noticed, it's important because it tells you what is inside and outside of a mesh, right? Because, I mean, if you have a surface, right, it's not clear what is inside and outside the surface, right? And the normal, it's a way to clarify this distinction. I mean, if you see an object, it's clear in the real world. But in the virtual world, you have to clarify that, right? And depending on the order, it's inside or outside. There is another way to represent the mesh, and I will go quickly on this because this is not implemented in Three.js. And as I said, there is a lot of other like relationship, and there is other way to represent the mesh. So beside indexed mesh representation, which is all you need for your project, okay? But it's important that you know that there is also alpha edge representation. If some of you will work with, will go and work in programming for a CAD, you go to Autodesk, you go to Adobe, you go, I don't know, some company that produce a CAD, and you will use some library. Most of them, if they do like geometry processing, what they have alpha edges, right? So alpha edge, you can imagine an alpha edge as a tripole of vertex, edge, and face, right? Is an oriented edge, okay? And each alpha edge has its siblings, which is the edge that goes on the other direction, okay? And it stays on the other face. It's derived by this fact, right? So imagine this is an alpha edge and this is another alpha edge, right? And then with this representation, what you can do, given an alpha edge, you have a lot of relation that you can do, right? I don't want to go in how this is implemented, but what you can do is like you have a pointer to the face of the alpha edge, you have a pointer to the siblings of the alpha edge, so it means the alpha edge goes in the other direction on the opposite face. You have a pointer to the next and to the previous on the same face, and of course pointers to the vertex, okay? So, and then you can actually do a lot of nice things because, for example, if you want to find what is called vista relations, right? Vista relation is like give me all the vertex that has that are my neighbors, right? So how I do? So for example, I start with an alpha edge, right? Outgoing from this vertex, and then I get the first. Then what I can do is like I go on the siblings, right? And then I go on the next, and then I get the other vertex, right? And then I continue doing so. Yes. So when you see this operation, usually it's referred as surfing a mesh, right? It's not like the surf that you guys do in Australia. It's much more boring, right? But it's also interesting. So it's called surfing a mesh. It means like how you actually or navigate a mesh. Surfing or navigate, they say, right? Because you actually sometimes need to move and to solve these queries on the mesh to some geometry processing. If you in future you do some modeling with me or some other guy for your thesis or PhD, so you will have a lot of this. You will see a lot of this in your life. Anyway, so this is a sketch of a data structure. So again, you have vertex and face, okay? But for each vertex, you have one emanating alpha edge, right? Because, for example, for this query, if I have just a pointer to the vertex, I need at least a point to retrieve the first alpha edge, right? And then the same for the face with edge. And then you have a list of alpha edge which tells you like the vertex that has been instantiated on it. So the vertex, so alpha edge is an arrow. So you have the vertex where it starts, the arrow. Then you have the previous and the next alpha edge, right? So for example, let's say this one. So let's take alpha edge number 0. Okay. So the next one is 1. You see, like here you have 1, this one, and the previous one is 3. Okay. You see? And then actually the V start is 0 because it's this one. Okay. You see it emanate from here. And then the opposite of this one is 6. Instead, if you go to the opposite, is 6, right? I didn't have any space. So you see this table, you can actually understand how alpha edge are, right? And with all this is the most compact way to represent a mesh with all the relation that you need, like vertex, 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 vertex edge, face, face, without the need of additional structures, okay? So this is the most efficient way to navigate the mesh. Again, this is not implemented in 3JS. 3JS there is indexed mesh, which is the most common case for interactive application of games. This is very useful for modeling. Okay, then you have all these adjacency relation, and okay, as I said, we have indexed and alpha edge. So good things of indexed is like it's compact. It's very nice, it's easy to read, right? Like 2 vectors, and it's good for rendering, and it's but sometimes it's difficult to navigate the mesh, right? If you want to get from a vertex the set of star of vertex, or from a face the adjacent face, so you need to construct some additional structure. Otherwise, on the other hand, you have alpha edge, which are good for navigation, for mesh processing, but the rendering it may be difficult, and it's a lot of waste of space. It's not difficult, the rendering, it's the fact that it's not defined for that, right? Because it's a lot of extra space you need. Sorry, there is a bit of Italian. Yeah, alcune buone librerie means some good libraries. Okay, I will change it and update on the web. So maybe the Spanish can understand better, right? It's quite similar. Anyway, so it means some good libraries. So of course, I mean, you will use 3JS, but for geometry processing, there is the VCG library, which is the library that I also developed with the guy in Italy. It's an open source project, and it's part of the MeshLab program that you downloaded, that we developed in Italy. OpenMesh is from Germany, and Seagull is from French. So yes, they are good, but yes, I don't know. I think I prefer VCG because I actually did, and I program and I know how to use it. Not because of the fact that, yeah, because I'm Italian and the other from France and Germany. It's like that. Okay, so Seagull is the most, to be sincere, Seagull is the most complete one, but it's very, very, very difficult to use. I mean, when you have to write program in Seagull, it's tough, but it's nice. And of course, there is for geometry processing, there is MeshLab. That if you see on my video again that I put on the web, I will open MeshLab to load the mesh and decimate it, and to save in another format. And MeshLab allows you to do some basic operation, for example, smooth a mesh. So if I have this mesh, I want to get something smoother, okay? Or yeah, in this case it's another kind of mesh that you can smooth. Or you can denoise, right? Sometimes when you scan a model, you have noise. You can erase the noise a bit, right? And denoise. There is some algorithm to do denoising. There is much more than that. There is also what is interesting to you, maybe it's simplification, which is called quadric edge collapse decimation. And you can actually reduce the size of the mesh of triangles, trying to keep as much accuracy as possible, right? And of course, this is automatic. Yeah, so this is a bit of overview of all the mesh models. You have, as we said, like surface or volumetrics. For surface, we have different kind of representation. What we are interested in to us is triangle mesh and polygonal mesh, but of course you can have range scan. Range scan is when you actually do a scanning of an object. You have for each point of view a depth value that tells me from this point of view how depth is the point on the 3D, right? And that gives you like a 3D shape. This is what actually the Kinect does, right? It gives like a range scan. And then, of course, you can have much more continuous like subdivision of parametric surface. We don't care about that. You have point cloud. And for volumetric mesh, there are the ones that I show you, like CT scans and stuff like that. But there is maybe also sometimes, instead of having, so as you use triangle for representing a surface, sometimes you use tetrahedral or cubes to represent volumes, right? I don't want to go into details, but these are useful for some other applications. What we are interested on is this, okay? File formats, okay. There are some competing standards, and then, oh well, we need to develop the universal standard that covers everyone, yeah, and then there is another one. So this is what happens. So that means that there is always people struggling to create a new standard for represent. As I said, there is OBJ of FF, but there is tons of them, right? So there is always somebody coming out, oh no, we have to make it like one standard, and then in the end, people like keep using the standard, old program, and then you have another standard, right? So there is a lot of formats, right? A lot. There are maybe more than this, right? This is some of the one I know and I found like around, and yeah, it's a Tower of Babel, right? You know, like the legend where there was like this tower where everybody speaks a different language and stuff like that. But the difference is like, so they differs for various things. So they usually triangles and polygonal mesh. Some of these formats, for example, for 3D Studio or other things, they also have the coordinates of the cameras, or the light environment because they're supposed to be used for rendering. This is not the case for us, where we are actually creating our rendering environment, but you have to know that. Some of them, they have based on alpha-edge, they're based on indexed, or they have direct representation as the one for the printing, right? They have triples of coordinates. They can have per face or per vertex attribute. If they have just per face, then if you want to do like a smooth rendering, then you have to average on the vertex, right? As I explained in the previous lesson. And some of them are difficult to parse, other like are very some are simple, other are difficult because they pretend to be very, very general, and they end up like being crazily difficult, and some of them are binary, other are ASCII. And so here is like some of the models, right? And yeah, it's not important that you know about that, but it's just when you navigate and do find some models around, then it's actually what I suggest is to use OBJ or Ply. That I know there are the importer in 3JS. So for example, I use Ply. If you download an OBJ and then transform the OBJ into Ply using MeshLab, and in 3JS, what you have to do is, and remember that I did like 50 minutes video that I show you precisely how to do so. So the idea is like you have to include the Ply loader, right? Ply loader is also OBJ loader. If you want to load an OBJ, it's part of the library. You go online, you download it, and this is also in my basic package on my exercise, right? On my examples online. There is this plyloader.js you have to include in your application, and then you actually have to load a mesh. You have to just call this loader.load, and this returns a geometry, right? So, and then what you do is like you can see this example on my code or on the video. What you do is like you actually create a mesh, and then with the geometry, so this function returns you a geometry, which is actually the set of triangles and the set of vertices. You remember when you create a box in 3JS, you create the geometry box, right? And then you create mesh with that. So this is the same. Instead of being a box, is the geometry of the 3D model. What you have to do is like you have to compute the normals, right? Because otherwise your shading will be bad. You won't see a nice shading. And what you have to do is like sometimes these mesh are huge. They are placed somewhere randomly in the space. What you want to do is maybe scale and move in front of the camera. So which means transforms object coordinates to world coordinates. You remember I explained this at the very first lesson. And what you can do is like how I can understand where the object is located in the space in 3JS. So the standard way, and you will see in my lecture on the video on YouTube, so it's like you can use the bounding box. Bounding box is actually it's an axis aligned box that contains the object, okay? And this is very useful because it gives you the size of the object and where the object is located in the space, right? So this bounding box has a minimum and a maximum. And you can get the center of the bounding box, which is roughly the barycenter of the object. You can get the sides of the bounding box, which is the diagonal of the bounding box containing the object. Given that, you can actually use that to scale back the object and to translate in front of the camera. So then you can actually translate in front of the camera and scale of the right proportion while you loaded the object. Okay, this concludes for now this lecture that has been recorded.